Hello everyone, we are the database group from Tsinghua University. Today we will present our work, interactively discovering and ranking desired tuples without writing SQL queries. Let us start with the introduction of our problem. This paper aims to help users discover a set of desired and ranked tuples through interactive exploration when precise SQL queries are hard to specify. Informally speaking, given a relational table T, the user wants to find the answer R, which is Qt of an unknown SQL query Q, where the term unknown either means that the query is too hard to specify or the data is unknown to the user. Let's illustrate through an example why specifying such SQL queries is hard. Suppose a user wants a new manual petrol car that is produced after year 2010, not provided by commercial sellers, and its brand can be either BMW with price less than 10,000 or Volkswagen with price less than 8,000. Moreover, assume that she wants all cars to be ranked by a weighted sum function minus 0.018 times price plus 0.98 2 times power. But note that she does not know this function. That is, the ground truth query can be expressed as Q1 below. Q1 is hard to specify because there are complicated predicts in the where clause, including and, or, not, and range selection, and it is hard to provide the weighted sum function in the order by clause. Then let us review the prior auths and their limits on solving the above problem. Keyword search allows the user to retrieve some desired tuples by providing some keywords. Query by example aims to infer users' desired tuples by user-provided examples, either desired or not desired. Partial orders for tuple ranking ranks tuples based on user-provided partial orders for tuple pairs. But 1 and 2 only discover desired tuples denoted by decision problem, and 3 focus on ranking all tuples denoted by ranking problem. There are also methods that find and rank tuples, such as a SQL synthesizer, but can only support simple ranking functions. That is, no existing work can support the above complicated case in Q1. Then let me give an overview of our system, dexplorer. There are 2 parts of dexplorer, front end and back end. In the front end, it will interact with the user in multiple iterations until user budget is used up or the answer cannot be improved. In each iteration, you will allow 2 operations. You can click to annotate a tuple to be either true or false, or drag to annotate that one is ranked higher than another. The answers annotated by the user are then transformed to a set D of true or false labels of the tuples, and a set R of partial orders between pairs of tuples. Moreover, in order to address the cold start problem, we allow users to pose a few keyword queries to quickly get some desired tuples here. For example, for Q1, the tuples T1 to T4 are labeled as true, so they are in D plus. T5 and T6 are labeled as false, so they are in D minus. And for the ranking problem, T1 is ranked higher than T2 and T2 is ranked higher than T3, etc. In the ith iteration, the user will provide feedback to the backend. The backend needs to address 2 problems, answer inference and question selection. The answer inference is to infer the result by user's feedback, and the question selection is to select key tuples for the user to label in the I+1 th iteration. Okay, let me give a demonstration of our system. This is the main interface of dexplorer, where you can annotate tuples and view recommended tuples. In the data type, you can choose a dataset or load a new dataset. Let's choose the core dataset as an example. Suppose our unknown SQL query is Q1. To quickly start, search manual petrol. Then we can start annotate tuples here. This tuple is bad because its brand is Mazda. This is bad because its year is less than 2010. This is bad because it's commercial. And this is bad because it's Audi. The left tuples are good, and we annotate them as true. Then we drag those tuples by the hidden ranking ground truth. Click the Recommend button. The system will show us the recommended tuples, where we can see most of the tuples are good and well ranked. You can download them as CSV, or you can continue typing if you are not satisfied with the results. After 3 iterations, we can get these recommended tuples, where the top 10 tuples all satisfy our hidden decision intent and are well ranked by the ranking intent. After system demonstration, let us turn to the back-end algorithms. First is about the decision answer inference. The decision problem is a binary classification problem. Deciding whether a tuple is desired or not, we use random forest because it is more robust than decision tree and it has interpretability. Finally, it can provide diversity for tuples, which can be used for the question selection. For the ranking answer inference, we should think about how to rank tuples. The answer is by a linear scoring function. Dexplorer assumes users' ranking intent can be expressed by a weighted sum function ft equals to wt, which is a common assumption in many data exploration systems. Thus, Dexplorer uses ranking SVM to learn W. Besides, inspired by the GBDT plus IR model in many commercial IR systems, we developed a hybrid ranking model, LambdaMart plus ranking SVM. The LambdaMart model outputs a transformed feature double code T for each tuple single code T, and T equals to single code T concat double code T is fed to ranking SVM. Then ranking SVM outputs a weight vector W for ranking. Then let's talk about how to do question selection. In each user iteration, we need to select a list of key tuples from a table T for user to label. We should select tuples which the machine learning models are uncertain about, and those selected tuples should be as diversified as possible. For the uncertainty of a decision question, we define the uncertainty of a tuple T as the entropy of the predicted results of all decision trees in the random forest. For the uncertainty of a ranking question, given a pair of tuples Ti and Tj, the ranking SVM model learns a parameter vector W. Then, the model is uncertain about the tuple pairs whose absolute value of WTI minus WTJ are close to 0. Let the single quote Vt be the predicting vectors of all trees in Rf for tuple T, and let double quotes Vt be the transformed feature of tuple T output by the LambdaMart model. We use Vt, which is single quote Vt, concat double quote Vt to compute the diversity. We define the similarity S of tuple Ti and Tj as Sti Tj is cosine V Ti Tj. After the definition of the uncertainty and the diversity, we can define our question selection problem. We want to find a set S star with k tuples, where the tuples in S star have the least decision uncertainty, and the tuple pairs in S star have the least ranking uncertainty and similarity. The formal definition is shown in definition 4.1, and the question selection problem is NP-hard. We propose to first solve the problem by only considering uncertainty and then incorporate the diversity into the solution obtained in the first step. When we do question selection without diversity, the equation 1 can be resolved to equation 2. Suppose S contains T1 to Tk, and Wt1 is less than Wt2, Wt2 is less than Wtk, then we have equation 3. We sort T by Wt in ascending order and obtain a sorted list T equals to T1 to Tt. Use Tm to denote the prefix of list T with length m. Let's define Smn as the optimal solution of selecting n tuples from Tm. Then we can write the corresponding dynamic programming equation and solve the question selection problem without diversity by dynamic programming techniques. When considering both uncertainty and diversity, we optimally choose tuples with high uncertainty by the above dynamic programming algorithm. But when adding a tuple T to the result set S, we check whether T has a high similarity with existing selected tuples. If yes, we just drop it, else we include it to the result. We compare our method with state-of-the-art solution for discovering and ranking desired tuples, cycle synthesizer. We test 2 cycle queries Q1 and Q2, and figure 3 shows the effectiveness of the 2 methods. from where we can know that cycle synthesizer only supports simple hierarchical ranking function and has a poor performance on complex ranking function. dexplorer performs better than cycle synthesizer on Q2, which is due to the effectiveness of the question selection algorithm in dexplorer. So that's all. Is there any question?